In this video, I will explain you oscillation of a magnet in a magnetic field. So let's say we have a magnet in this way and kept in a magnetic field. So first I will explain you what will happen when a charge, a positive charge is kept in an electric field. It will experience a force, right? So what will be the amount of force? Q into E will be the amount of force. Similarly, a magnet, when it is kept in this way, north pole will experience a force in this direction along the magnetic field. Like positive charge will be experiencing a force along the electric field, but if you are keeping a negative charge, then it will be experiencing a force in the direction opposite to the direction of electric field. So north pole, that will be in this direction FP, and here south pole, it will be in opposite to the direction of magnetic field FP in this direction. Now similar to the quantity Q, we have in this case, we have magnetic dipole strength here. That is magnetic moment here. Sorry, not magnetic moment, magnetic strength. So we have magnetic strength here, M. So how can I get the value of magnetic moment from magnetic strength? We know M is equal to magnetic moment is equal to, in the case of electric field, it is P is equal to 2AQ. So similarly, here in this case, instead of 2A, we will have 2L here, and instead of Q, we will have pole strength. So Q and pole strength is analogous. Electric dipole moment and magnetic dipole moment, they are analogous. Okay, so here the total force will be, here in this case as it is QE, what is analogy of Q? M. Analogy of E, magnetic moment. So this will be, magnetic field. So this will be M into B here in this direction, and here it will be M into B in this direction. It's a dipole, right? When we are, it's a coupled, right? When we have a lid to be opened, we will be rotating force in this way, right? My thumb is pulling it upward, and my index finger is pushing it downward, correct? With the equal forces. I am applying force here and also I am applying force here. So it's a couple here in this case. So how to get the value of torque produced by a couple? That is any of the force in the perpendicular distance between these two forces. Now this is one line of action of the force, and this one is another line of action of the force. In between the line of action of the force, find the perpendicular distance and multiply with that. Okay, now let's say the distance is, the total distance here is L. I will take it as 2L, okay. 2L, because for dipole moment, magnetic dipole moment, we have taken the distance in between M and M as 2L, right? So I'm keeping the same 2L here. So it's 2L. Let's say the angle is theta. Angle in between the magnetic dipole moment or the magnetic moment. What is magnetic moment? 2Lm. So that will be in this direction, and magnetic field is in this direction. So the angle in between these two, if it is theta, then this 2L can be split into two directions. This one is 2L cos theta and this will be 2L sin theta. So 2L sin theta is the perpendicular distance, 2L cos theta is the parallel distance. So perpendicular distance and parallel distance. Anyway, 2L cos theta is not required here. We only require 2L sin theta. You can use the basic trigonometric properties, like this one is cos theta. You have to find this distance, and this distance is not. You can use, this one is theta. So you can use sin theta is equal to opposite by hypotenuse, then opposite is equal to this into sin theta. So that is 2L into sin theta here in this case. Okay, now I got the value of distance in between these two line of action of force. How to get the value of torque now? Torque is a couple here. Couple is equal to any of the force. So Fp into distance in between. What is that? 2L into sin theta. Now what is the force? Fb is equal to pole strength into magnetic field. How did we got this equation? That is the analogy. Because we already have learned the equation for Fe. So Fp can be taken, taking the analogy of each term, that makes Fe is is equal to mb into 2L sin theta. Now, what is 2L into m? Dipole moment, magnetic dipole moment. So this will be mb capital M. Now I am going to substitute m into 2L as capital M. So m into b into sin theta. So m into b into sin theta can be written as m cross b. So this is a vector. So torque is also a vector. This is very important. Now, so what will be the result of torque? Result of torque will be rotational motion. What is the result of force? Linear motion. Result of torque is rotational motion. That will rotate now from this position to this. But actually that will try immediately rotate here. But with the inertia it won't stop here. It will come down. So like from magnet in this position, it is having a torque in this direction. Okay, so that will immediately rotate in this way. But here it won't stop. With the inertia it will go here. Now it will get a torque in this direction. It will go here. Then it will get a torque in this direction, come here. It will get a torque in this direction. So this is an oscillation here. Okay. Now we will see whether it is SHM, simple harmonic motion or not. But as of now it is an oscillation. Okay. Now how we will check whether it is oscillating in simple harmonic motion. So for what is the property of simple harmonic motion? Acceleration should be directly proportional to displacement. Okay, and the direction of acceleration should be opposite to the displacement. This we have learned in the last year. And we also have got an equation, acceleration is equal to minus omega square x. And omega is equal to angular frequency. We know the equation 2 pi by 2. You can just go back to your class 11 oscillations. These are very important equations. Acceleration is equal to minus omega square x. Anything in this format, I could say that is executing simple harmonic motion, where omega is equal to 2 pi by 2. Now I will substitute the value here. So acceleration is equal to minus. So from here I will first get the value of omega. What is the value of omega? So see here, this is with the direction, right? So I am going to only consider magnitude here. I don't need direction as of now to get the value of omega. So omega is a number, right? Angular frequency. So that will be a divided by x. Omega square is equal to a divided by x, where a is acceleration, x is the displacement. So omega is equal to root of a by x. Omega is equal to root of a by x. So what is omega? Omega is equal to, from here, omega is equal to 2 pi by t. So 2 pi by t is equal to root of a by x. So I can get time period from here. Time period is equal to 2 pi into root of x by a. I will take t here. I will take root x here, root a here. So root of x by a. This is very, very important. But I can use only this equation to find the time period if that is executing simple harmonic motion. So first I have to prove that this one is executing simple harmonic motion. Then I could use this equation to get the value of time period. What is time period? Time period is nothing but for this object, for this magnet to oscillate one complete cycle. How will that be? From here till here, then coming back to this position. That is one time period. Then second time period, third time period. So first I have to prove this one, that acceleration is directly proportional to displacement. But here in this case it is angular acceleration, torque, right? So if it is rotational motion, then instead of this I can prove alpha, that is angular acceleration, is equal to minus omega square. Instead of x, that will be theta. So in the case of linear motion, that is displacement. In the case of angular motion, that is theta, angular displacement. And acceleration will become angular acceleration. So here torque is equal to, I can substitute torque as, first F is equal to ma, you know, right? So what is the analogy in rotational motion? Instead of force we have torque, instead of mass we have moment of inertia, instead of acceleration we have angular acceleration. So torque I am going to substitute as moment of inertia into angular acceleration is equal to m cross b. So angular acceleration is equal to md n cross p divided by moment of inertia. So I'm going to m cross p, I'm going to open, that will become md sin theta divided by angular acceleration. Now for small angle theta, when theta is very less, okay, when small angle theta, I can say sin theta as theta. Only for small angle. So for small angle, I can substitute this one here. It comes here. With that sin theta, I am going to consider it as theta. So md by I into theta. Now see this equation here. See, alpha is equal to m p theta by I. See, we have proved the case. Why? We know moment of inertia of a specimen, that is the constant. Magnetic field of the source, that is constant. So this one is moment of inertia, this one is magnetic moment. So magnetic moment of a magnet is constant. Magnetic field intensity of a source, that is constant. I, moment of inertia of a specimen, that is constant. So all these are constants. See, alpha is directly proportional with theta. See, acceleration is directly proportional to displacement. So here in this case of angular acceleration, that is acceleration directly proportional to theta. Then obviously, see, the direction will be opposite. That is the reason. See, when it is displacing in this direction, see, at this position, the velocity will be maximum. Okay. Now as it comes down, the velocity keeps on decreasing. Right. See, as it comes down, as it makes a positive angle theta, but velocity is decreasing. Just visualize. Now from here, it will speed up, it will come to here. Now from here, it will go to the other side, but velocity gradually decreases. And at here, that will become 0. Then that will go in forward direction. Then, so what is happening when it is going to the extreme case? From here, we are measuring theta, right? When theta is measured positive, but the acceleration here in this case is negative, correct, which means velocity decreases. So when theta increases here, what is happening to acceleration? Acceleration is a negative value, which means velocity decreases. See, theta positive, theta become higher and higher, velocity decreases to 0, and this is what happening here. So it is that is opposite to the displacement and directly proportional to the angular displacement, that is theta. So this one is simple harmonic motion. That is very important. Now if it is simple harmonic motion, I can substitute this equation here. What is the equation for time period? 2 pi into root of x. X is nothing but, here in this case, it will be theta, angular displacement, divided by a. So here it is acceleration, we have to consider angular acceleration here. So from here, I can get the value of theta by alpha as transfer I and mb this side. So I by mb. So this will become I by mb. I'm going to substitute theta by alpha here. Theta by alpha is equal to I by mb. So how did I got the value of theta by alpha? From here. So this is the equation for time period. Okay, this one is very important. And I will also give you, so we got the value of time period. Now we got the value of torque. We will also try to get the value of potential energy. Okay. So I am rubbing all this. Torque we require, so I am keeping torque here. How we will get the value of potential energy? How does the magnet is going to store potential energy? See, let's say it is going down. Now from here it is going to, here it is having high velocity. From here it is going to decrease velocity. The next position is in this way, right? In the oscillation, in between these 2 points, that is oscillating. So from here velocity decreases and finally it becomes 0 here. Which means potential energy gradually increases and the whole energy will become potential energy at this point because here velocity is 0. Now from here again potential energy decreases and becomes 0 here. The whole energy is kinetic energy. Then again velocity decreases and becomes 0 here, which means the total energy is potential energy here. Now how does it build potential energy? How does the potential energy is being increased? That is due to the work done. Okay, so we have learned that work done is equal to force into displacement. Now in rotational motion, work done is equal to, instead of force we will use torque, instead of displacement we will use theta. Now torque at each and every position is different. See the equation, mb sin theta is the equation for torque. So when the value of theta changes, torque also changes. So torque is different for different theta. So we can't multiply in this way. For the total potential energy, we have to integrate because this is a variable torque. So work done by a variable force, we know that integral f dot ds. This is the work done by variable force. Now this is variable torque. How it is variable torque? With respect to theta, value of torque changes. Okay. Now come back to this. So we have, this is d theta. So let's say from with the torque, it is going to have a small displacement of d theta here. From here, d theta here with a new torque. From here, d theta here. So we have to add all of them to get the total potential energy. So potential energy is equal to, what is the value of torque? That is, I am going to substitute from here. What is that? mb sin theta into d theta. So m and b is constant, right? I can take m and b outside. What is integral of sin theta? That is cos theta. So the equation will become minus of mb cos theta. So this one is nothing but minus m dot b. Okay. Now the other thing is very important. Torque and potential energy of different for different angles. So theta is equal to 0, theta is equal to 90, theta is equal to 180. Tell me the value. Which equation you will use for torque? Torque is equal to mb sin theta. Now which equation you will use for potential energy? Minus mb cos theta. This is a very important question. Okay, to find the value of torque and potential energy of different position. So torque, when theta is equal to 0, sin 0 is 0. So this one is 0. So when the magnet is parallel to the electric field, there is no torque. But is there potential energy? Yes. What is the value? Cos 0 is equal to 1. Potential energy is equal to minus mb. Okay. In the next case, when theta is equal to 90, sin 90 is 1. So this will become torque is equal to mb. But what will happen to the potential energy? Potential energy will become cos 90 is equal to 0. Okay. Now, how we will get the value of potential energy? When theta is equal to 180, sin 180 is equal to again 0. So torque is equal to 0. Now what is cos 180? Cos 180 is minus 1. So u is equal to minus m into b into cos 180, that is minus 1. So that will be mb. So you can get the value of maximum potential energy. What is the value of maximum potential energy? That will happen when, see, when north pole comes here and south pole comes here. This is the case of maximum potential energy. Here in this case. Now what is the case of minimum potential energy? When that is exactly the opposite. That is, so I will mark magnetic field strength in this way, and here in this case north is here and south is here. So this is maximum potential energy. Now minimum potential energy is this one. So where north is here, south is here, and magnetic field is in this way. Make a note of it. Thank you.